And it's good that you're close to it.
Yeah. Are you all set?
Yeah, I'm ready.
Hi everybody, welcome to London Text Analytics. Hope you're all comfortable. So straight to some people here. So we've got two talks for you tonight. The first one's different in the sense that our first speaker has no slides, which is a good thing. He's going to do everything live and it's all live coding, so we're going to start no smoking mirrors. So that's lots of fun, and that's still Gooch, and he's over there.
Hello.
And we've also got our second speaker, Bharathi over there. He's going to talk about recurrent neural nets and probably lots of heavy maths that I don't think is great stuff. So we should say a couple of thanks. Thanks to Hertz for stepping in at the last minute in helping us have a conversation with Gravitas Recruitment. So a round of applause for Gravitas Recruitment. Very kindly arranged for us to be here. Right? It was fantastic. So, we're very grateful.
Oh, that was a pleasure.
Thank you very much. And check out Gravitas. It's a great company. Some of the services we have.
No, I'm not here to pitch now. Depends on my time.
All right, excellent. So I think we've got, as I said, two talks about 30 minutes each. If you're all set.
Okay, I'm going to come over here to start with. I'm going to go back there. My laptop's connected to the projector, and I'm going to do some live coding, so I'm going to do that. So you'll just hear my voice. So I'm Phil Gooch. I've been involved in this text analytics group quite a few years, although it's been some time since I remember. Thanks very much, Tony. Great case for inviting me. So I've been doing text analytics on and off for about 10 years. And this is something I've recently discovered off databases. So it's fairly new to them. It might not be so new to you. Some of you might know this stuff already. I was quite excited to find how you can use graphs and graph databases to do some common NLP tasks. I was previously doing it a different way. Using things like word to vec. Using that sort of graphing way with word similarity tasks. People tend to use the cooler approaches like word to vec. Which is maybe easier to understand. It's nice to see how it fits together. So I thought to put together this talk I'm using here today of graph approaches to do NLP and analytics. And there's probably enough material here to cover a half-day workshop, and I've got half an hour. So I won't be covering everything, but there'll be some links to sort of further reading. So I'll look back over there and carry on talking. So graph, there's kind of two competing formalisms for modelling graphs. There's one that's it's been around for a while, which is the RDF graph, which stands for Resource Descriptor Framework, and I seem to have lost my signal. There we go. So in the Semantic Web world, some of you may be familiar with ontologies and Semantic Web. This formalism has been around since about 1999, and it's a way of modelling relations between objects in a way that can be serialised in a kind of XML type serialisation or various serialisations, and stored in something called a triple store, which can be thought of as a graph database. So in this representation, we've got this concept of an object, a concept called detective, and that has properties of has first name. So we've got an instance of detective, first name Sherlock, surname Holmes, and then this detective investigates a case, and this case has a title called A Scandal in Bohemia, and this detective lives at an address. And what you'll notice is that these relations can point to other objects, but they can also point to string literals as well. So this is kind of a weird thing about the RDF graph model, is that it's like a subject, predicate, object model, but the objects can either be just literals or they can actually be proper objects that have properties themselves. So there's kind of a little bit of what's the word? Not inconsistency as such, but you know, the thing at the end of the edge can either be a literal or it can be another object. Whereas in the property graph world, which is the area we're going to be looking at tonight, as used by databases such as Neo4j, the property graph, you have fewer edges because your edges only connect true objects. Any property of an object, this is why it's called a property graph, live as a feature on the object. So rather than having a relation called has first name and has surname, as we've got here for Sherlock and Holmes, we have a detective who has a property first name Sherlock, he has a surname Holmes, and then there's a relation lives at an address and investigates a case, and the case has a title. So it's just a different way of modelling it. I'm not saying one is better than the other, but they both have their strengths and weaknesses. What's strong about the property graph approach is that you can do things like shortest path between things, which is quite hard to do in the RDF world. I don't think the Sparkle language, which is used for querying these type of graphs, actually supports finding the shortest path between things, whereas the graph databases such as Neo4j do actually let you find shortest path between objects in the graph. So we'll be using some of the shortest path stuff tonight in some of the NLP tasks that we'll be looking at. So I just thought I'd show this slide as a difference between kind of two competing modelling formalisms for modelling text and relations between text in a sort of graph format. And this was kind of interesting as well because there's a minor Twitter storm happening at the moment about this, where somebody who works for Neo4j is in an argument with somebody who's been doing RDF and triple store modelling for many years about whose formalism is better and which one is a true graph or not. So I just thought I'd put that out there. But if you want to follow Neo4j on Twitter, you'll see the argument kind of taking place then. So, okay. All right then. So first thing we're going to look at is an algorithm called TextRank. Now, TextRank is basically based on Google's PageRank, but applied to individual words rather than web pages. And what it basically does is look at how connected two words are together by the other words that they tend to be co-located with, and then it applies the PageRank algorithm to that. Now, all the information in this presentation is 95% of it actually comes from other sources. I've just kind of tidied it up a bit. So I encourage you to read on the GitHub link that I posted to the group these three sources here. So Josh Bode's blog post on using TextRank for document summarization is really good. And then these two presentations on using Neo4j to do other cool NLP stuff are really good as well. And I've taken their code and I've just sort of cleaned it up a bit and made it work with Python 3 and the latest version of Neo4j. But there's more stuff in there, particularly on opinion mining and how to use that within Neo4j, which is really cool actually, so it's worth checking that out later. So let's just look at TextRank and within we'll look at Neo4j as well at the same time. So I'm just going to start up a Jupyter notebook and let's just have a look at some code. Okie doke. So what I've done, I'm going to create a new notebook and redo this from scratch. So I've created some code here which I've put up, and maybe you've had a chance to look at it already, and I'll just talk you through that. So I've created this TextRank object, and what it's basically going to do is load a file. It's going to run it through a TF-IDF vectorizer from scikit-learn, and that's basically just going to turn the words into vectors and do some TF-IDF reduction on them so they're weighted according to inverse document frequency. And then it's going to split the tokens into sentences, and then it's going to basically convert them into a bag of words matrix. So what we're going to get is we're going to get a matrix where the rows represent the sentences and the columns represent words in the TF-IDF matrix. And what's going to happen here is, this is kind of standard collaborative filtering. We're going to create a similarity matrix from that. So we've got a matrix that consists of words in sentences, and we're going to multiply that by its transpose to get a similarity matrix for the sentence. So what that's going to do is multiply all the entries in the words row by the column in the transpose matrix and give you similarity between words in each sentence. And then we're going to do the opposite of that to get similarity matrix between the words themselves by just flipping this equation the other way around. And then we're going to do some magic with NetworkX, which is a nice Python module for doing graph-based stuff. And it's going to turn that into a graph, and then we're going to plot that graph, and we're going to run the PageRank algorithm on it to find things like what are the key sentences and what are the key words, and have a look at how that works in the graph. Hello.
Sorry, maybe I'm missing something. What is on the entry in the bind of words matrix? Is it an index corresponding to a word?
Yeah, so it'll be so imagine you've got 100 words, so there'll be the entry in the 50th column will represent the 50th word as ranked in alphabetical order. On there. And there'll be a score, and there'll be a way to touch to that about with its TF-IDF weight, the weighting of that word within the corpus of the whole. And then we'll do the same for the sentences as well and multiply them together. Yeah, sorry, I kind of skipped over that bit.
No, I don't.
Okay, great. So let's load this up then. So funny way that Python works with its packages now. Okay, so I'm going to load something relates to the previous slide, which is the text of a scandal in Bohemia by Arthur Conan Doyle, one of the Sherlock Holmes cases. It's not the whole text, no, it's a sample of it. So these are kind of toy examples because I didn't want this to take too long to run. So in the real world, yeah, you obviously have bigger corp. And you wouldn't run this via Jupyter, you'd have this in some sort of parallelized process as well. So what it's doing then is going to run this code, it's going to set up these matrices, word similarity matrices, and it's going to calculate the page rank on both the sentences and the word graphs. So let's have a look what it's given us. I'm going to do the top 3 keywords. So as you know, if anyone is familiar with the case of Scandal in Bohemia, it's about Sherlock Holmes encountering Irene Adler, I think for the first and only time, who's involved in a blackmail case against the King of Bohemia, and he manages to track her down. I can't remember much about the story. So the top 3 keywords kind of give us a nice little summary about what this case is about. It's about Holmes, about a case, and a woman. And then what are the key sentences in the book? So we do key sentences, top 3. So to Sherlock Holmes, she was always a woman. I'd seen little of Holmes lately. As I passed the world, I remember God, blah, blah, blah. So these are considered to be the most important sentences in the story, based on the co-occurrence of words in the sentences and the relative weights between them, and carrying out the sentence similarity matrix between those 2 matrices that correlate the words with the sentences.
Does that mean important in a prototypical sense?
Important in a page rank sense. So if you imagine weights attached to each word in the sentence, and words that tend to that are similar in context to other words in that sentence will get a higher page rank. So what happens is when this goes into a graph, you imagine you've got words with various weights, and those weights get added to the edges between those 2 words in the graph. So we've got consecutive words. Each of those words gets connected in the graph with the weight of the word as the weight on the edge. And then the PageRank algorithm is calculated from that. So when I show the graph, it will be a bit clearer because you'll see how these are connected. So let's plot the word graph first. It's going to look a bit messy because it's going to be quite dense. And these are indexes into the matrix, these numbers here. What you get with PageRank, it's not necessarily the words that are the most connected that are the keywords. It's the words that are connected to the most connected ones. So if a word, in the same PageRank, it's not necessarily the web page that has the most links going to it. It's pages that are linked to other well-linked pages and both link out and link into those. So let's just have a look, put in some of these numbers here. So if I do get word, you can't really see it on that screen, but let's just have a look at one of those indices. So let's have a look at word 32. It looks quite well connected. Is it 32 or 33? Case. Okay, so that's good. So that one, I'm just pointing my cursor, I don't know if you can see my cursor, that is actually word 32, sorry. So that's a well-connected word. It's connected to words that are connected to other words. And then we've got, let's have a look at ones that also connect to case. Let's have a look at 127. See what word that is. Little. Okay, that's not particularly relevant. Let's have a look at one of the other ones. 118. No. Okay, so you can't just go by just eyeballing it particularly well to get what the keywords are, but you can kind of see how words that are generally well connected tend to be more important than others. That's basically how PageRank works. So if I do the same with the sentence matrix, if I plot the sentence graph, so it's much sparser because we've only in this excerpt I think I've got about 28 sentences maybe, I think, or distinct ones anyway. So let's have a look at one that looks quite well connected to others. I think it seems to be sentence 18 looks quite important, doesn't it? Yeah, and that was actually one of the key sentences we picked up by PageRank. Okay, so this is a toy example with a relatively small piece of text, so it's not going to work brilliantly. Obviously, the bigger the corpus you feed into here, you're going to get hopefully better results that have a wider vocabulary. I mean, there's quite a small vocabulary in this excerpt from this book. So this is using TextRank, which is actually using PageRank basically to find keywords and key sentences in a document or a corpus. You can use it with a single document, which is generally what it was used for. So it was a way of finding, if you've got a single document without a bigger background corpus, then you can use this to find keywords in that document, just solely treating that document as a corpus of sentences, effectively, and also use that to do a brief summary of that document. And this is a really basic implementation, so I'm not using any part speech features. I've stripped stop words out, but I'm not looking at any kind of lemmatization or normalization or anything like that. So it's basically lowercasing everything, stripping out stop words. So if you've got plurals in there, then they're going to be treated as separate words. So you can obviously improve this. You might want to include part speech information in there as well. You might want to weight nouns and adjectives more than verbs, for example, because you might not be interested particularly in verbs. You might only be interested in nouns for key terms. But this is a very simple implementation that comes from the Josh Bode blog, and using graphs to do keyword extraction. It's quite a nice algorithm. I'll take questions.
Sorry, this is really good, but how does it scale?
It's a good question. It's a good question. So I'm recently new to this approach of doing text analytics. So this is really using this Network X library for Python. I've no idea how well that scales.
Well, the PageRank scales for TextRank, that's the same idea as the Spark graphs anyway.
Is it? So you could do PageRank within Spark.
Certainly more to get
access to the generalized one, yeah, they easily have
Okay.
But their stuff currently at the slightly smaller amount of scaling, they're scaling okay without even generalized.
Okay.
For a long time, they were always talking about that.
So
every time we went to the meetup.
So basically, if Spark supports PageRank, then you could apply PageRank to the Word and document similarity matrix in a parallelizable way, and maybe that would work. So maybe that's something to try and present in the future.
I think that's the question. How does this compare to other embedding, word embedding algorithms like?
So this isn't a word embed. So this is so word2vec will do similarity between words that will tell you, that king is to queen as man is to woman. But what this approach tries to do is to tell you what are the most salient words in the document by virtue of their interconnectedness with other words, or what are the most salient sentences. I don't know if word2vec will actually let you use the algorithm to do keywords and key sentences. I mean, maybe there is a way of doing that, but it's a slightly different use case, I guess. But the stuff,
But it's pretty based on collocations, which are asymmetric. I mean, if A collocates with B. I mean, PageRank is one directional, whereas the PageRank here is if it's just collocation, it's kind of asymmetric. Is that right?
Yeah, that's a good question. Yeah, I don't know the answer to that.
So therefore, it's slightly different to PageRank in the traditional.
Yeah, possibly.
Right.
So it might not be directly equivalent because, like you said, the direction is important. So we're going to go on to Neo4j now, where the direction you can actually model the direction explicitly. So you can have a bidirectional link or a unidirectional link. And we'll do a similar thing there with that, where the actual direction is. Use a directed graph rather than bi-directional.
Just the other story. Without using different sentences, you do the same other story.
I wouldn't go that far, because a lot of the I've got the full story here, we could actually try it. The trouble is, a lot of the story is dialogue. In fact, 99% of the story is actually dialogue. If you take out all the stuff in quotes, you only end up with about a dozen paragraphs. So the dialogue might skew that in terms of what the summary is going to look like. But we could try it if you're interested. If you've got time.
Actually, my point is a bit long, but Python was originally supposed for summarization. So there was one idea of actually extracting the most important sentences and extracting summary.
Okay, so I've done it on the full text. Didn't actually take much longer. So the top three keywords now are hone, said, and man. And you can imagine why said is in there, right? Because it occurs loads of times in all the dialogue. Let's just expand that a bit more. I say it's a very naive implementation of text rank because we're not adding any features to it at all. It's just the tokens themselves. It's not. There's no lemmatization going on. So we've got said, photograph, king, no, street, room, majesty, house. So it's not particularly informative when we add all the dialogue in. And similarly for the sentences, let's have a look what we get. Yeah, so we get said homes. For some reason that's appearing twice. So I don't know how useful that is when it comes to which is interesting how it kind of falls over a bit, doesn't it, when you start adding lots of dialogue into it.
But for use, it works well.
Yeah, I would imagine.
For this,
Okay, so that was just an introduction. This is kind of a run into the main thing, which is the Neo4j stuff. So if we move on to that, because I'm sure, Udo, you know a lot more about page rank and text rank than I do. This is all very... I'm presenting this because I was quite excited to find this. But it's not... It's not. What exam? All right, so let's have a look at Neo4j. So Neo4j is a graph database. It's very easy to install if you have a Mac. You literally just do brew install Neo4j, which I won't do because I've already got it, and then you do Neo4j start, and you're up and running basically. Then there's configuration for memory and threads and so on. It's very easy to use. So I've got an instance of Neo4j running, and let's load some text into it. So I'm just going to load a couple of sentences in here and do a similar sentence similarity thing. So I'm not going to go into the syntax here. There's loads of tutorials online about the Neo4j graph syntax. But basically, I'm loading in a bunch of sentences from that same story, and I'm creating a graph with a next relation where one word follows the next. And you can see it's a directional graph where word 1 is followed by word 2 in the next directional relationship. So I'm going to load that in there. And then I'm going to do it for another one. There. Then we can see the sort of thing that results. So we've got explicit follower relations between words. Let's just get that to show a bit better. So, yeah, so you can see the words there. So this is really naive. There's no stop word removal, so we've got words like in, there, in there, for example. But you can see how in those group of sentences we've got word-follower relations on what word tends to occur next, or what word does occur next in that collection of sentences. And each next one has a count, so how many times the weight, if you like, unnormalized, and then the count of how many times the word always, for example, appears, eclipses, and so on. So most of these have a count of 1. So now we can run some queries on that. So let's do a shortest path thing between homes and emotion. We're always told that homes doesn't have any emotion. So okay, so this is all the shortest path. So it's not just a single j, which is quite nice between those, which we can do here. The other thing we can do is look at frequency of word pairs. So again, we're saying match a word that's followed by, has a next relation with another word, and return the values of those and the counts of the next relations between those, and then order them. So if I do that. So again, most of these are stop words. We've got of and his appears 7 times, of and there appears 7 times, his and there appears 4 times, and so on. So we could extend that with trigrams and n-grams in general by expanding that query out. So that's just quite a nice way of using the graph database to do this kind of collocations and counts on how frequent these pairs occur together. So let's have a look at a bigger data set now. So I'm going to load in a bit more. So I'm going to just clear this. Any questions on that though to start with?
What's the integration of the shortest path?
I don't know, I just thought it was something that interesting to apply, but on its own it's probably not that useful unless you've got a lot of words in your database, in your graph database, and you've removed stop words and maybe lemmatized them and maybe added some weights as well, based on other features. So as a raw kind of measure, maybe it's not that useful on its own, but where it is useful is in the bit I'm not going to cover today, which is on opinion mining, where they basically use the shortest path to find do abstractive summaries of opinions from a collection of reviews on products, which is one of the things I linked to. So they do use that. You had a question?
Yeah. Like looking at the syntax, it looks like it has some similarity to SQL.
Yeah.
Not completely, but do you comment on your experiences in that domain?
So the main bit to get used to is the syntax of the object model itself. So the first, you kind of prefix you say, well, this is the type of thing I want to look at, and you give it a variable name. And then you have your features in curly brackets that you want to match. So this would be like a where clause, effectively. You find a word where it has a property string of homes, another word that has another string called emotion. And then you've got a function. So this bit is quite unlike SQL. This is almost like, I don't know, almost like an XPath type expression in a way, isn't it? Yeah, so it is some of it does have it has where clauses. You've got count and order by, as you have with SQL, but the matching syntax is more a kind of path type syntax rather than a sort of SQL column matching syntax. And you have these things here where you've got next star. So that's saying that this word is followed by this word. I haven't actually made this directional, by the way, so this can go in either direction. And star means any number of steps ahead, which is a quite nice way of saying it. They don't have to be directly followed by the other. They could be any number of steps between them. If I make this directional, then we'll probably get different results. So I'll just put a little arrow on there saying this one has to go in that direction. And we get we get a straight line between homes. Homes, she, eclipses, and a strong emotion. So that's doing a unidirectional shortest path between homes and emotion. It may be scattered across a number of sentences. So these might not actually directly follow each other. There might be an intervening word here, just that it's gone. There may be other. This is the shortest route, but there may not be a direct connection between these in the sentence. You probably wouldn't find a sentence that has that. So the stuff I mentioned on opinion mining, which is on the link on the GitHub repo, on the graph notebook one, there's one on opinion mining. That's exactly what they do. They use that to abstract away from all the opinions to find sort of pseudo sentences and pseudo phrases that summarize those opinions as a whole, and it actually works quite well. Maybe we could look at that on a future meetup, but I haven't really got time to cover that one today. Because on its own, home, she, eclipses, and a strong emotion is a bit of a nonsensical sentence on its own, but maybe with enough data, those kind of gaps get ironed out, and with a bit more sophisticated matching, you can get something that kind of reads more like a natural sentence. Okay, so I'm going to clear this, and I'm going to look at some of the code in the other class where we load a slightly bigger data set. So let's go back to the notebook. Okay. So I've created this class called Neo for Graph, which is basically the code that's in here, but I've kind of made it, just encapsulated it a bit really, so that you don't have to see all the steps that are happening. But basically what it's doing is a whole bunch of queries here, which I won't go through right now, but it's basically going to load the sentence, turn it into an array by lowercasing it, stripping out white space. It's going to get rid of punctuation, such as quotes. It's going to remove stop words if the stop words priority is set, so it's just going to take all the NLTK stop words out, put it into a list of tuples, and then it's going to load that into Neo4j in a similar way as we saw with that shorter example, with the follow-on relation. This word follows the next word. And then it's going to calculate two relations. It's called left and right. So the left query basically says, find me the word that precedes my given word, and the right query says, find me the word that comes after that. Now, it's a very naive implementation of collocation because it's only finding the immediately preceding word and immediately following word. But it's using that to find some kind of similarity measure between words based on how many words they have in common that both precede them and follow them. So it's doing a Jacquard similarity between those sets of words. So we'll see that in practice in a second. Let's just load that up. Okay, so if I just do that query here, so if I replace word here with homes, so you'll see that all the words that are to the left of homes are little, attention, see, and Sherlock. But it's only one word along, so it's only the immediately preceding word. So it's not. We can have to modify that query if we want to go 2 words back and 3 words back and get the whole set of them. So we have a similar query for the rightmost word, and then basically this collection of words here, plus the ones that follow to the right, will be used in a Jacquard similarity to say what is the similarity between homes and another word in the corpus, and to look at the overlap between those two sets, basically. So it's a really, really basic way of doing it. And so there's no kind of weighting involved. It's just an example of the sort of things you can do in Neo4j. So let's run that now then. So so what it's going to do is calculate all those Jacquard similarities between every pair of words in the corpus. And what it's doing, then we can run a query to see what are the most similar words to a given word. I didn't write a function for this one, so I'm going to have to paste the query in. So basically say, find me where the word is, I can change it to Bohemian. Where the word is Bohemian, it's related, has a related to relation to another one. So this related to is going to be scored by the Jacquard similarity of all the words that it both precedes and follows. So it's going to be a Jacquard score on all those related to relations. It's going to order it by that score. So we can find that sex is the most similar word to Bohemian in this particular document. And then we'll say, okay, what are the topmost 100 related words? So look at all words with a related to relation, which would be the Jacquard similarity, and give you the top 100. So we've got mention and vague. Well, I don't know. Predominant society. So sex and Bohemian, I mean, they're kind of related, aren't they? Arguably. So because this is quite a small document, a lot of these words don't really have a lot of semantic similarity, only by virtue that they tend to co-occur with other words. So in a similar way to word embeddings, you get better results the more data you throw at this. So with a very small collection of, a few hundred well, not even that, about 20 sentences, you're going to get poor results. But it's just to illustrate that we can do this relationship extraction based on the co-occurrence of co-located words that occur before and after the keywords that we're looking at. So again, we can do a query on following words and shortest paths. So let's have a look. So with this corpus, stop words have been removed, so that maybe the path will be a little bit better. So let's have a look. So the shortest path between Holmes and Irene Adler is this one, so homes, always, woman, late, Irene, Adler, and emotions. But it's a circular path because I haven't made this directional. So again, if I make this directional by putting the arrow in the query, then it has to go in a single, this will be a linear relation now. So it should be this. Homes, always, woman, late, Irene, Adler. So this gives us a connection between those concepts by the words that tend to connect them. But again, as it's a very small corpus, the results don't make a huge amount of sense in this context. It's just really just to illustrate the sort of things you can do if you load your corpus into a graph database such as Neo4j, and it has this quite nice query interface that lets you do this. You don't really have to write any code. You can just write these types of queries and it will give you the result. And obviously you can make this more sophisticated by adding more features to that. So we've kept it very simple. So just a number of toy examples based on these blogs and posts that I found quite inspiring as I came across these only about a week ago, and I thought, well, a couple of weeks ago, and I thought it would be just interesting to put some code together and demonstrate it and have a play with it, and just thought I'd present that to you today for your interest, and hopefully maybe it's something you want to follow up on and follow up on those posts and take further than I've done here. So thank you very much.
Any questions?
Richard.
Hello.
Hello.
I've been reading about some work about embedded graph modeling.
Yeah.
Vector space items produced by the web. Don't really have much experience.
No, I don't know.
It sounds like an interesting area. You can have surrounding it are words, tokens of similar similarity.
Yeah,
And then you don't need to have a direct link to the part.
that's right.
You can just query and within a certain threshold to any concept that happens to formulate code.
Yeah.
But yeah, I was really enjoying it. So I was going to ask
I haven't got experience with it, it makes sense. So going back to the earlier stuff on text rank, so those matrices are sparse matrices, whereas with word embeddings it's going to be quite dense matrices. So it'd be interesting applying those matrices to the similarity matrix and applying page rank to that and see how well that works. And maybe similar here with the with some kind of measure of what words follow on and what words co-locate, and doing some kind of Jacquard similarity. I mean, here it's just Jacquard similarity between those sets of words. Maybe there's other measures you can do. If you can create a query for it, you could probably do something like that. But I haven't done this. But something to. Yeah, and maybe there is, unless you already looked and not found them. But it would make sense. So yeah, definitely. Good idea.
Then